Let's start with a little philosophical. What do you mean when you're solving a problem? What do you think you're trying to do when you're solving a problem? Yeah, remember, key of computational intelligence is that computer can find intelligent solution that you can't. The reason you can't is not because you're stupid, it's because you can't imagine n dimension, and you can't work with data that's 10 bazillion entries long, right? Intelligence means finding solutions, right? Solution to a problem. So what exactly do you mean by solving a problem? I would maintain that you're doing this kind of thing. And this is something you never hear from anybody else. But I would say something like all problem equals to inversion. Huh? If I give you a little puzzle and I say, right, AX equals Y. Okay? Now, if I give you A and I give you X, and ask you what's Y, that's not solving the problem, that is plotting. Yeah? So, this is X, this is Y. This is X, this is Y. You're not really cracking anything, right? There's no mystery there. You're just plotting, basically. Well, what if I say that's x1, y1, x2, y2, and I ask you, what's the equation that gives you this two set of points, this set of 2 points, right? So I'm asking, what's the A that gives you this y when I give you this x? What's the A that gives you this y when I give you this x? Right? So it's not plotting. It's not taking x, A, I give you y. Right? So in a way, what is the A? What's the A that gives you that? So the forward path is easy. It's the backward path. When you end with the result, you've got the result. Right? But you want to know what exactly gave rise to that result. That is the key of problem solving scientific. Right? That is the challenge. That's what makes you intelligent. Right? If I get you, that's in high school, right? X plus 2, x minus 3, right? And ask you to multiply it out. Right? That's very easy to do. But if I want you to mentally factor, right? And x minus 6, you two factors. You have to say, what is it? Give rise to the end result. So you're doing the inverse. Okay? So all problem solving is inverse. That's what makes you intelligent. By the way, that makes me, let me take a minute to say, well, I never bought this saying that a lot of younger generations say something like, well, he's smart, but he's cheating, or he's smart, he's clever at cheating. You're not clever at cheating. Cheating just means you kind of go through the shortcut, right? It's not difficult to identify the shortcut, but you're honest, you're not cheating, you're not going through the shortcut. That's it. So I never find this saying that this guy is smart or this politician is intelligent, but he's corrupt. If you are corrupt, that means you're not intelligent. You can't solve the problem, right? You have to find a shortcut. So I always say that the people who are dishonest are stupid. Yeah? The solution looks clever, but all it is just exploiting holes. Like if I'm going straight, it takes a long time, right? Because it's a straight. But if I transform myself to a little rat, then maybe go through the hole. Well, there's nothing clever about making yourself be a rat coming into the hole. I know where the hole is, I just don't want to go there, right? Well, the difficult problem that I would qualify as intelligent is actually solving the problem. And say, I want to get here. What gets me there? It's not a shortcut to get here, that's cheating. But it's what's the ingredient? Now, I use the word inversion because I guess in English that's the more familiar word. But mathematically, you usually use the word inverse. Okay. So, why am I talking about inverse? You thought I was going to talk about linear algebra, right? Why am I talking about inverse? Okay. Well, once again, see, once you get me going on the blackboard, it's very hard for you to bring me back down to doing things on the, it's very clumsy. Much faster to do things. Right. So, I asked you, I give you y equal to ax as an assumption. And I give you the value of y, I give you the value of x. And I ask you, what is the a that when multiplied by x gives you y? That's trivial, right? So, what's a? What's a? It's 0.55x. Now, I'm going to change the notation a little bit. Okay? Ax equal to b. Now, I told you that I'm kind of switching the role here. The x here is the previous. Y is equal to ax. And I ask you what this is, right? So, this case, I'm going to ask you what the x is. X is equal to b divided by a, right? Who disputes that? It's a very good thing. That means you're catching a little grasshopper, but you actually get on a war elephant to do that. Okay? This is brilliant. It's the most powerful tool in mathematics. You do easy things the hard way. Let's do easy things the hard way. I know that this is the answer, right? It's trivial. But this is what I'm going to do. I'm going to ask myself, is a equal to 0? I'm going to ask myself. If the answer were yes, what can I say? What can I say about x? Come on. This is not algebra. This is what? It's deeper because you have to think about it. Come on. If I ask you what is a, is it equal to x? Yes. And what can you say about x? You can say two things. X is impossible, or any x will do. Why is that? What makes x impossible? Well, if b is not 0, you can't, right? You can't multiply 0 to something and get non-zero. It's impossible. What makes anything will do? B equals 0. Because anything multiplied by 0 gets you 0, right? Okay? This is great again. Right? You're getting on a war elephant, catching a little grasshopper. Okay? Next, you ask, okay, what is it? No, it's not equal to 0. I ask another question. What is it that multiplies by a gives you 1? What multiplies by a gives you 1? 1 over a. Or the inverse. Did you do that? Yes, because a is not equal to 0. Okay? Now I know this. I keep this. And I say x is equal to whatever is the inverse of a multiplied by x. So that's equal to 1 over a times x equal to x over a. Oh, sorry, b. No, not your pattern. Okay. Silly. D, right? See? You can do this in your sleep, right? In one step, right? But how many steps did I take? A whole bunch of steps. Yeah? Is it more fun? It is more fun. Is it more useful? It is more useful. Because you can only do this when x is a scalar. You cannot do this when x is a vector. Right? Can't do that. All the steps, all the linear algebra, well, all the undergraduate level linear algebra, all the first semester of undergraduate linear algebra is about this. Okay? It's this long-winded step, but you do it in a general form. Okay? I'll give you the terminology right now. Right? When I ask this question, actually, I'm asking a different question. I'm asking, oh, is the determinant of this thing equal to 0? No. If it is, then look at the right-hand side. Yeah. If it isn't, find the inverse of A. So are you with me so far? Right? Right? So all of linear algebra is this. Now let's step up the game a little bit. We can. I wrote a little something that you can look at in Mathematica. Okay, Jono. Document, work, guys of Basai, second class, Mathematica, logical, and data analytics, machine learning. Right. Oh, we have to share the screen. Screen. Yeah. Now, the first thing that I'm not going to teach you that you should know is how to do a dot product. You know how to do a dot product, right? Please. A dot product. Well, what's A times B? AB, right? Well, what if A is not a scalar? You know this notation? Right? A is a real number, right? Any number from minus infinity to plus infinity, right? Well, what if I have x is R2? That means actually x is equal to x1, x2, right? Right. Yeah. Now, what if I want y is equal to y1 and y2, and I want to multiply them together? What makes it? What's the physical operation? Well, the reason I said I hope I don't have to cover this is because it's fundamental. Okay. If x is R2, y is R2, okay, what you have to do is make one of them lie down, like F transpose Y. That's the dot product. X1, X2, Y1, Y2. Now this is all I want you to know from high school. This is more than 1 month. You have to know this. Right? Yes. You can't multiply A, B, and C, D together. You have to make one of them flip. And when you flip one of them, it's no longer dimension n, it's 1 by n, right? So these are the basic objects that you will know. You need to know. A is a scalar. Yeah. If it is 1, right? In fact, it doesn't have to be a real number. It can be counting number, right? Like number of people can be partial, but it's fundamental. Okay? X is a vector if it's dimensional n. Now, by convention, we are, well, human beings, right? We like to stand upright. So by default, X stand up straight. Right? If you are lazy and you want to lie down, okay? You're not human. By the way, they're not channel means sideways. So, literally, that's it. Your spine goes sideways. That's the ancient word. So if you want to go sideways, then that's channel. This is what you do. Take the transpose, right? And your dimension is 1 by n. 1 by n. Okay? Those are the basic objects. Okay? So basic, I have to do it. Okay. Now, to distinguish this upright human from pronated person, I will call it X transpose or row vector. Yeah. In fact, this is the default way of storing your data in Excel, right? Yeah. You go down, it's a vector, 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 vector. It's all row vector. So how many? So you need one index to tell you which element, right? Now, last night I expect you to, honestly, how many of you didn't go through the video I asked you? Come on. I want to see honesty. Who hasn't seen watch the video? Who has? Okay, good. Who hasn't? Be proud. You've done something wrong. Be proud. Okay. Okay. I am proud to have been silly. I won't be silly anymore, sir. Okay? If you watch that, I wouldn't have to spend another 5 minutes. Okay? Right? So that's a vector. What's that? Now, this vector is what you need, right? You have one index. If, for example, in the video, you say, from a data perspective, a vector is just a list of numbers, which it isn't, but it's a list of numbers. Let's say x equal to u, right? And x1 is your height, 5 feet 7, okay? And your weight is, I don't know, 130 pounds, something like that, right? Now, technically speaking, when you talk about vector in mathematics, it's the same unit. But if you think of vector as this list of numbers, then this is something like 5.8 and 130. You can say that's a vector. So this is a number, right? So if I want u, this is u. If I want your height, this is x1. This is 5.8, right? Now, so how many index do I need? I need this one index to say which element I'm talking about. But what about if I have something like this? x11, x1n, xm1, xmn, m row, m column. Right? This is a matrix. A. You use generally you use big capital A for matrix. Dimension is m by n. Right? M by n. So that's the matrix. Now, eventually we hear of things called tensor. Where does the tensor come from? So how does tensor come in? Well, if you think about it, a good example is this. Your computer screen, right? I can, for individual pixel, right? If you have that resolution for say the 650 by 80, right? I can access individual pixel by saying how many times, how many pixels I go down, how many I go across, right? So I only need I need two indexes. One is high, one is j, right? Right? And that works for black and white screen. Does it work for color screen? No, it doesn't, because there's another layer, right? So you need a third index, k, where k can be 1, 2, or 3. Let's say 1 is red, 2 is green, blue, 3 is green, right? So you need R, M, N, L. That's a tensor. And that's cheating a little bit, but it's tensor from computer science point of view, from general relativity. Any of you guys physics deep or anything? No. You know how Einstein? You know what Einstein? Funny memes that you see. Well, this more than just a meme. Really? Okay. Well, he's saying that the gravity works by distorting the space-time. The space-time is just coordinate, right? So coordinate. If you talk about general dimension, you have not just 3 dimensions, you have time as well. So you have 4 dimensions. Okay? So it's not x, y, and z. You have actually t. Well, what's clever about that is not only does he do this, he said this thing can be twisted in a calculus way, becomes differential geometry, and the Earth actually distort the space-time. So he adds calculus to tensor. Well, he doesn't add it, so he uses that. That's how brilliant he was. Anyway, that's physics, definition of tensor. But in scikit-learn, well, not scikit-learn, but in some kind of Keras library or TensorFlow library, okay? In image processing, you see TensorFlow because your data is tensor because it requires 3 indexes. It's the pixel, go down, pixel, go to the right, and then the color. The 3 numbers. Right? 3 numbers. You find your, and you need all this. You need all this to paint a picture. So that's why your iPhone facial recognition thing works off of tensor, because when it takes a picture, it takes color picture, right? So color picture is a combination of red, green, and blue. Okay, as you adjust that, turn the value. So it is a tensor. So that's why all the iPhone thing works off of tensor. Tensor is a generalization of matrix. This is a generalization of a vector. This is a generalization of a scalar. Right? Scalar, sometimes they call it dimensionless. Dimensionless. Right? Your math is scalar. It doesn't have a direction. I can look at you this way, you have the same mass. I can look at you that way, you have the same mass. But your dimension, right? The dimension, say your speed, that depends on the. So those are the basic objects. And all I expect you to remember from high school is want to multiply 2 vectors together, they have to have the same number of elements, and one of them has to lie down first. Right? And the other thing I expect you to remember from high school is you can multiply matrices together, right? As long as what? The left matrix and the right matrix, right? As long as this dimension matches that dimension. So if this has m row, k column, and this has k row and n column, when you multiply, what happened? This, you do it one at a time, right? Right here, here, m time, right? But we also do it with the second column, n time, right? So two matrices can multiply if the second dimension of the first one on the left matches with the first dimension of the right. Now, in particular, we are going to do this a lot. We are going to make scalar, vector, and matrices. So chances are you do a lot of this. This thing multiplied by that. So it's m by n, and then n by 1. Right? And then you get this. Right? Now, if you don't have that, you can have this as well. This is m. This is m, n, and then you get 1 by m by n is 1 by n. So you have row matrix. So if you lie down, you're always on the left, right? You stand up, you're to the right. Okay? So you can multiply matrices to matrix, two matrices together, matrix to a vector, a row vector to a matrix, a row vector to a vector, and you can also multiply element by element. That's just scalar. Now, by convention, and all over their place here. By convention, scalar, you use a Greek number, like alpha. Okay? Then, for vector, you use a small alphabet, like X. Okay? In physics, or in mathematics, they usually make this a boldface. In physics, they usually have an arrow on top because, as you saw in the video, okay, physics represents, in physics, usually represents an arrow. And capital, not boldface, is the matrix. Tensor, I think it's the same. Right? So there. You can almost see that if I write something like this, AX, what I mean is alpha x1 xn, which is equal to alpha x1, alpha x2, alpha xn. Right? Okay, that's the basic currency of this data. That's all you need to know. Now, in the next 5 minutes is what I hope you knew, but I'll still give you insights into what you do. Let's restrict the case. Let's restrict the case when a matrix is squared. Okay, so it is n by n matrix. What's nice about matrix, a square matrix, is that when it multiplies by a vector, dimension n, it doesn't change it, right? So it kind of lives in the same dimension. Now, you can imagine, yeah, what kind of animal are you? Well, what kind of being are you? Three-dimensional being. So actually four-dimensional, but you can't visualize that, right? But imagine that there's also a two-dimensional animal. Yeah? Animals that live on a flat plane. Yeah? Well, fortunately, you have higher dimensions than that. Okay? So, if you're standing over here, being perfectly three-dimensional, okay, and I do something to you, you would hope that you still stay a human being, right? Maybe somewhere else. So you would like to stay three-dimensional. Yeah? Well, if I multiply you by a 2 by 3 matrix, you become reduced, right? To a two-dimensional animal. If I multiply you by a 4 by 3 matrix, then you become a superhuman in 4 dimensions. Well, we're talking about human-to-human transformation. So we're going to talk about square matrix. Okay? Now, the restriction makes it easy to imagine, but also is fundamental to what I talked to you earlier about finding a solution. Now, maybe the last thing that I kind of hope you knew, but maybe I should expect you to know. What if I write something like this? A, B, C, D. Instead of, you know, if normally, if this is big A, right? The notation is little a, A11, A12, A21, A22, okay? But because the two-dimensional matrix is used so often, a lot of times I just write A, B, C, D. I hope you guys don't mind it, right? Now, if I do this, x1, x2 equal to, well, the dimension is going to be 2 by 1, correct? But I'm going to call this y1, y2, or most of the time, I would call it b1, b2. And the reason, one of the reasons is that in a lot of time, a lot of text, I would just call this x and y. Right? Okay? So you can imagine, you can either talk about this, x1, x2, or x and y. Right? And if I have a number, say 3 and 2, it's that point. Right? Yeah, physicists would think of it as an arrow. Okay? You would think of it as a list of numbers 2 and 3. So, but I'm going to use x1 and x2 because I can show that. Now, what does this represent? It is a puzzle. Yeah, it is a puzzle, right? It's a puzzle. So, first imagine what I did before. This is the beginning of the class. Writing the element. 4 elements at the middle. But, right? If this were a number, set of number, this were a set of number, I want to find out what x is. Right? So my problem is to invert this thing. So it's like what we did before. I asked something about this. Is this thing equal to 0? I want to ask something like that. Except I don't ask that. Yeah? Because it may not be 0, but still fail. Yeah? And then I'll say, is there a way I can say something multiplied by A, B, C, D is equal to 1? Except when you can't have a 1, you must have something that has the right dimension. And I call that a 1. Well, what should that look like? 1, 1, 1, 1? Well, that's no good. I'll tell you why it's no good. Because the property of 1 is that it multiplies something and it doesn't change it. Right? Now, if I have a 1, 1, 1, 1, I have kokai and kokai. I don't get kokai and kokai on the right hand side. Right? Because I get kokai plus kokai. And I get kokai plus kokai. This is no good. But if I did this, just keep 1 on the diagonal, that will do the trick. Because it's kokai times 1, kokai times 0, that's kokai. Kokai times 0 plus kokai times 1. Right? So this thing is the same. So what I want is some guy that multiplies this and equal to that. And then x1, x2 is equal to that guy multiplied by b1. And that guy is called inverse. That's the notation, right? It's basically a 1 over. What you want to do is you want to say x1, x2 equal to b1, b2 divided by the matrix. That's what you like to do. You can't do that. Okay? You can't put the matrix at the bottom. So you have to find something that's the inverse. So that's the long-winded way of saying I need to find the inverse. Okay. So I think if you have this from high school, you're pretty good. You're pretty good. But do you know why? This is why I don't expect you to know. Well, if you think about it, if I multiply this out, let's multiply this out. AX1 plus BX2 equal to B1. Right? How do I get B1, right? That's the thing, right? So B1 here is this thing, right? Just this is how you calculate. This is how you calculate. So this is CX1 plus DX2 equal to B2, right? This is how you calculate. But if I don't want you to look at this as a whole object, I want you to look at it one at a time. What is that? That's an equation. Come on, guys. That's an equation. That's quality. Okay, must be an equation. Right? What's that? What's an equation? Remember? You try to solve. Originally, you had a very simple equation. Right? You're solving an equation. Except now, this is a matrix equation. But essentially, when you write it all out, you have two. I can call this scale equation. Just to emphasize the fact that it's not a matrix. Yeah? This is a scale equation. This is a matrix equation. Right? But it's dimension 2 by 2. So when you break it down, it actually has two equations. How many unknowns? Two unknowns. Right? Remember, this is a coefficient, so I know this. I just haven't put it in. This is a parameter. You guys haven't forgotten, right? What I told you about parameter and variable. What's the difference? Maybe I haven't. A variable is something that changes in that context. A parameter is something that doesn't change, but maybe for a different problem I would change it. Right? Think of it as different questions on the test. Right? If I say, you know, you get back to grade school, I say, okay, 3x equal to 6. Okay? And I have to solve it. And I go to another question and say, 8x equal to 16. 24. Right? This is known. In that problem, this is a variable, right? You have to solve for it. So on the change value. But this thing doesn't change. But for a different problem, I can change it. So think of it as unspecified constant. Or constant you can change for another problem. Okay, that's called parameter. So variable is something that you can change in that setting. Parameter is, and for different problem, it may have different values. But for that value, it doesn't change. Same as physics. If you're on Earth, the gravitational pull gives you this, what, 9.8 meters per second square. That doesn't change anywhere on Earth. But on Mars, it will be a different number. So that is an Earth parameter. Okay? Right? But what changes is your velocity, your position, but the rate of acceleration to Earth is constant. Actually, technically, it's not constant, but for all practical purposes, you all share the same age. Yeah, 80. This one I would give to you as a real number, but I don't feel like writing a real number because it's not generalized enough. But this thing is still unknown. So it's a variable. In this case, X stands for unknown or variable. They use X or right. So now, fundamentally, you have two equations, two unknown, and you have sort of don't you have that 3 equations and 3 unknown, so forth? You know that, right? Well, technically, that's not very true. So what does it mean when I said, go back to original case, AX is equal to B and A is equal to 0? It's some kind of failure thing, right? Because it doesn't give you you have three things you can say about x. X has certain value, a unique value. Any value and no value whatsoever. That's it. You have three status. Okay? You can be who you are. You can be anything. You can be nothing. Okay? And the situation that is troublesome is you can be anything or you can be nothing. That's when A is equal to 0. Well, in this case, if this were all 0, that's also true. But there's also another way that can be troublesome. Anybody think of this? Well, first we have to visualize first. What does this mean? What's AX1 plus BX2 equal to B1? It is a line, right? Now, how do you plot the line? This is X2. Oh, sorry. This is X1. This is X2. What is that line? That line is equal to what? What's X2 in terms of X1? X2 equal to B1 minus AX1. Oh, I just made something terrible. This B and that B and another same B, sorry. Okay, let's call that Y. Bad. But we'll go back to B in a minute because we'll go back to A. Yeah? But let's do this. Okay, so this becomes your equation. Now, in this case, I want to solve this. You don't like this notation. Let's call it theta. Right. What is this equation for x? X2 is equal to theta 1 minus dAx1 and the whole thing divided by d. Right? Yes? Okay, that gives you funny look. Right? So what is that? That's a linear equation. This is a straight line, right? This is the intercept. And this is the slope. Right? So that's it. That's a combination of x1 and x2. Now, here's another combination of x1 and x2. x1, x2 equals to theta 2 minus cx1 divided by b. What's the coefficient? That. What's the slope? That. And then you solve for x1 and x2, right? There. Right? You've done this in high school. No, actually, you've done this in grade school. 2 equations and 2 unknown. Or maybe high school, maybe junior high school. Certainly, some kind of high school. Yes? You can do this, and you have done this. You might not know why or what for, but you will know now why and what for. So that's it, right? That's the end of the story. So what's the problem? No problem. I can solve for x. Well, what if I can't solve for x? There are 2 problem cases that I can get to. X can be anything, and x can be nothing. How can that arise? Well, when you solve the equation, you say x1 and x2 has to be on that line. x1 and x2 have to be on that line. And if you solve them together, it has to be on both lines, right? That's the intersection. Okay? Right? So what does it mean to have no solution? They don't intersect. Now, let me ask the second question. What does it mean to have any solution? Well, I don't mean any as in any solution, but non-unique solution. So I shouldn't say any solution, but no unique solution. Well, I can certainly have two lines that line on top of each other, right? Now, my question is, this thing is qualitatively different from both of us. Somehow A and B and C and D, they give you information that don't repeat. Thus, they give you information that repeat. The problem is the right-hand side. Okay? So if, for example, in A and B, and I put in A and B here, right? Definitely we get into trouble, right? Right? But what kind of trouble are you going to get into? Okay. I just made this happen. A1 x1 plus, sorry, A plus B x2 equal to theta 1. Correct? And I have A x1 plus B x2 equal to theta 2. See? Same line, right? But what kind of trouble do you get into? It depends on whether or not these guys are the same. If they are the same, they are the same equation. So you're just writing one equation into unknown. That's why you're not getting any solution. What if it's not equal? Then you write two equations, two unknown, but they're not consistent. You can't have both. You can't have A x1 plus b1 equal to theta 1 at one time. And when you do it another time, it gets to theta 2. That's indeterminate. Ah, it's a nice word. Right? So, I can determine unique value of x, or I cannot. If I cannot, it's because of two things. You have non-unique value of x, or x is impossible. Either way, it's not good. You don't like it. Remember, your problem is to find the solution. Right? This is not a solution. Yeah, just give you another question. Well, so what? We have this combination of x1 and x2. But which combination is the right one? I don't know. So the question is not answered. This one is even worse. It's saying there's no answer whatsoever. Okay, so you stop. So you can only solve this if you do this. So the fact that A and B are the same is what determines the case. So I have already given you, what do you call that when you embed something in the mean? One word is determine. The other word is solve. If you are going to be able to solve this, you have to determine that you don't have this thing here. Now let's be a little bit deceptive. What if I give you C and D? Right? C and D. But I tricked you. I said C is actually equal to 2 of A. And D is actually 2 of B. Have I made the situation better? No, I haven't. It's still the same multiple, right? So basically, what you want to know is whether or not you have something like this, say 3 and 7, yeah, and say maybe 21 and 49, right? Multiply by 7, get it? Multiply by 7. Now, how can I operationalize this in a computer? Well, I can say this is equal to that because the ratio is the same, right? Right? So, if the ratio is the same, that's a bad thing, right? 7 divided by 3 is equal to 49 divided by 21, correct? Okay. Now, let's do things a little bit. Let's say 7 equal to 49 times 3 divided by 21. I can do that, right? This is bad. This is all bad. This is checking for bad. And I put this, right? And I, instead of this equal to that, I say this minus this equal to 0. Can I do that? Yeah? Well, actually, I want to do the other way around. It's the same thing. Okay. So, it's this guy multiplied by that guy minus this guy multiplied by that guy. It's the zeroness of a matrix. Yeah? If you have a scalar, is it 0? Yes, it is 0. If it's a matrix, it's not obvious. There's a hidden zeroness in it. And how do you determine that? You calculate this number. Therefore, it's called determinant of the matrix A. And because the determinant is a scalar, it's a quantity that gives you zeroness, it's like a size. Sometimes they write it like this, like measuring the size, like a norm, like absolute value. So this absolute value of matrix is whether or not we're checking for size or zeroness. That's called determinant. Right? Now, I enjoy this a lot more than sitting there, but certainly, breaker. Okay.